the important parts of being able to sketch the function are the end behavior and the zeros. Everything else is really not that important. So the first thing you want to do is kind of look at the end behavior and factor and find the zeros. So here the zeros were 0 and 5, and 0 had a multiplicity of 2. X cubed was our leading term, so that tells me the coefficient is positive. So that tells me from the left, I'm going to negative infinity, and if I go to the right, I go to positive infinity. So I start down here, I approach 0, I don't cross it because it has an even multiplicity, the 0 here, even, so I touch it, go away from it, so I stay below the x-axis until I reach x equals 5, and then x equals 5 has a odd multiplicity, so I cross it, and that leads me up to infinity. You guys see that? Overall, end behavior and the zeros are the only thing you need to kind of sketch out the function. It's just a rough draft. I don't know, this might go down a lot further, but it's not that interesting. I just know it's between 0 and 5, it's below the x-axis. You guys, the next function was already factored for us, so that turned out to be nice. Comments here. So I got my zeros really easy. -1, -3, and 2 were zeros, so I post them. The end behavior would be 1/2 x times x times x, which would be 1/2 x cubed. So the end behavior is the same. Each 0 has a multiplicity of 1. So it's single multiplicity means I'm going to cross the x-axis. So cross here, and cross here. And I end up with my end behavior. Do you guys see that? Some of you are looking at like, no. So end behavior and zeros or what you focus on when you're asked to graph or sketch a function. This isn't necessarily the graph because I don't know how far it goes up or how far it goes down. The sketch is just interpreting the zeros and the end behavior. Here I can factor out an x squared, left with a quadratic, factor out the quadratic, I get x equals 3 and x equals -2 are my zeros, along with x equals 0. This is x to the 4th, so that is a end behavior from the left at infinity and the right at infinity. So I know I'm going to cross the x, or I'm going to touch or cross the x-axis at my zeros. So I cross at -2. I only touch at 0 because that has a multiplicity of 2. Do you guys see that? Multiplicity here is 2. So as I cross this, I touch it, go away from it, and then at 3 I cross it, and I'm back on the right side of the x-axis for my end behavior. Q of x, very similar. Factor out an x squared. Then I have to factor by grouping. And I end up with plus or minus 2 over 3, and x equals -2, and x equals 0. 0 has a multiplicity of 2 again, so I'm going to touch it and go away from it there. In behavior, x to the 5th. Coefficient's positive, so I'm going to look like this. I'm going to go down to the left, I'm going to -infinity, and the right, I'm going to infinity. Then single multiplicity zeros I cross, and when my multiplicity is even, I just touch it and go away from it. You will have something like this on your test where you'll have to sketch the function. So, yeah. Find the zeros. This one should have been pretty straightforward since it was already factored a little bit. Plus or minus 5, +7, and 0 are zeros there. So if you were asked to sketch this function, it should be relatively easy. The end behavior is going to go from -infinity to -infinity. On the left, -infinity, on the right, -infinity, because the leading coefficient's negative. And if I take x squared times x times x, I get x to the 4th. They all have single multiplicities, so I'm going to cross the x-axis at every root. Do you guys kind of see that? How you get to pick and choose the important parts of the function? And like someone said before class, a lot of it is just practice and exposure to these types of questions. And I don't know if Alex always does the best job with the graphing part. Here, this is kind of messy. The x-intercept or y-intercept, be very careful on Alex. They might change the order, right? Which kind of is annoying if you're used to the x being on top and then all of a sudden. So these were screenshotted from Alex. So the y-intercept is when x is 0. If I plug x equals 0 in this problem, I get y equals 0. So the point is 0, 0. But if I just want to know the y-intercept, I could say 0. That's all Alex asked for, 0. The x-intercept are the zeros of the polynomial, meaning if I plug in the x value, it will make the whole polynomial 0. So I have to factor here, factor out an x, and then I'm left with a quadratic, and factor the quadratic relatively easy. So my zeros of my polynomial are 0, 8, and minus 3. Here, my y-intercept is minus 18. If I plug x equals 0 into the function, I get minus 18. Sorry, that's my y-intercept. My x-intercept is what makes my polynomial 0. So this is a factor by grouping. Pull out a 2x squared from the first two terms and a minus 18 from the last two terms. And we get minus 3, minus 1, and 3 for our x-intercepts. Some of you just left this one blank, which it might have been not sure exactly what to do here. So choose the end behavior. This is minus 6x to the 6. So that tells me I'm going to fall to the right and fall to the left, right? Fall, fall. Some of you wrote it out and that was fine. Here, minus 6x cubed. That's going to rise to the left and fall to the right. So that's basically 4x to the 4th.
And that's the ones that are factored, that's the only ones you add all your x's.
Exactly, yeah. If they're not factored, you just look at the largest term.
What got me on those bottom two graphs, I was adding all the exponents.
And they were already, yeah. You only add them if they're factored. And like here, I have x times x times x gives me x cubed. Here I have an x to the 4th. There's nothing being multiplied by it. Here, write the function, write the interval in which it's decreasing. If you put minus 2 to infinity, that's fine. Minus infinity to minus 8, the function is decreasing. From minus 6 to minus 4, the function is decreasing. And from minus 2 to 0, the function is decreasing. If you put infinity, that's fine. Maximums. Local maximums happen at minus 6 and minus 2. If this was your function, what was the sign of the leading coefficient? Negative, right? The only way to get something like this is if my coefficient is negative. And then, which of the following possibilities for the degree f? 5 is the smallest, but any odd number would be fine. So 5, 7, or 9. Choose all that apply. 5, 7, or 9. Because you count the turnaround points. 1, 2, 3, 4. There's 4 turnaround points, so the polynomial has to be at least degree 5. So does anyone, this will be posted on Blackboard.
Can you explain D one more time? Sorry. How do you get how many?
So remember we said the n minus 1 turns. So the polynomial is degree n, has to have at most n minus 1 turns. So if you're counting the turns, you add 1 for the polynomial. So this has 1, 2, 3, 4. 4 turns, so it means the polynomial has to be at least degree 5.
At least 5 or more.
Mhm.
Okay.
And we know it's an odd degree because it's rising and falling. Yeah.
Okay.
And if they're doing the same, it's an even degree. But since one's rising and one's falling, or one's falling and one's rising, it has to be an odd degree. So that tells me it has to be at least 5, but it could be 7 or 9.
So you have to know the end behavior and the terms, basically.
I mean, the number of turns gives it away.
Okay. But the end behavior, doesn't that tell you whether it's even or odd? So you can...
The end behavior, that would give you the leading coefficient. Since the end behavior looks like this, the leading coefficient has to be negative. If the end behavior looked like this, the leading coefficient would be positive.
Like 5, 7, 9.
Because the number of there's 4 turns.
So I know, but like, why can't it be 6 and 8?
Because 6 or 8, the end behavior would be the same.
Oh, okay, so
right?
you do have to know the end behavior for this one to know.
To rule out 6 and 8?
Yeah. Okay.
To rule out 6 and 8, exactly. Because we know the degree of the polynomial has to be 5 or greater, and we know it can only be 5, 7, or 9 because they're on opposite ends. The end behavior is on opposite ends. That only happens with an odd leading coefficient, an odd power. Okay, so the 3, 4, where we kind of left off, it's important to be able to find the zeros of a polynomial. There's certain techniques we've talked about, factoring, using quadratic formula, factoring by grouping, things you learned in Math 110. And then we said, okay, we're going to apply this rational root theorem, and the rational root theorem gives you all possible rational roots of the polynomial, so you can start testing them. And they're in the form P over Q, where P is the factors of the constant term, and Q are the factors of the leading coefficients term, right? So this is a nice approach to say, okay, this is a cubic. I can't factor by grouping. Do you need a copy? Yeah. We're still on 3, 4, so if you weren't here Friday, I have extra copies of 3, 4. So we have 4 options. For an odd degree polynomial, one of the roots has to be rational. It has to be. And once you find one of the rational roots, then you have a quadratic, and you can always find the roots to a quadratic by using the quadratic formula, or you can test other methods if they're also rational. Turns out here, the other 2 roots were irrational. 1 and minus 1 wasn't a root. 2 was, but minus 2 wasn't. But this is a way to give you a list to kind of test that. We did this example where it turned out one of the zeros had a multiplicity of 2. So plus or minus 1 is the easiest thing to test if it's a 0, right? You can plug it in. And here we'd be taking 2 plus 5 minus 2 minus 11 minus 6. Or if I plug in minus 1, 2 minus 5 minus 2 plus 11 minus 6. If that equals 0, then that tells me minus 1's a factor. So then I can do synthetic division, and I've reduced this 4th degree polynomial to a 3rd degree polynomial, and I can do the rational root theorem on this polynomial. It turns out it's the exact same leading coefficient and constant term, right? Minus 6 and 2. So my zeros here are the same list that's given, and turns out I tested minus 1 again, and minus 1 was a 0 of this polynomial. So minus 1 was a 0 of this polynomial twice. So then I was able to factor the 3rd degree polynomial and got a 2nd degree polynomial. And then once I have a quadratic, I can use a quadratic formula, and it turns out they were still in that list. So you could have plugged in every number in that list and said, oh, well, 2 is a factor. Minus 3 over 2 is a factor. Minus 1's a factor. Minus 1's another factor. So that's where we left off, right? Did we list out the rational root theorem here? Then we just talked about it. Be the factors of 6 divided by the factors of 2. And it turned out listing them with their multiplicities. So this led us to the fundamental theorem of algebra. And the fundamental theorem of algebra states if you have an nth degree polynomial, you have to have n factors. Or you have to have n roots with multiplicities. So here we have a 4th degree polynomial, and we have 1, 2, 3, 4 zeros, right, with multiplicity. We don't really deal with complex coefficients and complex numbers too much. And if one root is imaginary, then there has to be 2 roots that are imaginary. Right? So they come in, they're called complex conjugates. If a plus bi is a root, a minus bi has to also be a root. Right? And that comes from the quadratic formula, a plus or minus the square root. If your discriminant, which is the number under the square root, if that's negative, then you have 2 pairs, right? A plus or minus that number I. So this is going to come in handy if they list 5 plus 7i is a root or a 0, then you know 5 minus 7i is a root. You get that for free. You guys see that? Because they come in pairs. They come in, they're called complex conjugates. So we'll kind of see how that is applied later on. Descartes' rule of signs is just a useful tool to say, do I have any positive roots or do I have any negative roots? So in this polynomial here, you see the sign changes 1, 2, 3, 4, 5 times. Right? The sign changes. So by using the rational root theorem, we can list out all possible zeros, which there's a lot of them. There's a lot of factors of 540. So we can use Descartes' rule of signs to show none of the zeros are negative. Because Descartes' rule of signs states, however many sign changes you have, that's how many positive zeros you have, positive rational roots you have, right? So I've taken this list and I've divided it in half because I don't have to test any negative roots because I know it's not possible. This is a 5th degree polynomial and I had sign change 5 times. Right? So this is what it means for sign change, and we'll look at this in some examples. This is a positive number. So from positive to negative, that's one sign change. Negative to positive, that's another sign change. From positive to negative, that's a sign change. So in this example, this is a 6th degree polynomial, and it has 3 sign changes. That tells me 3 of the roots are positive. You guys see that? Do you see the sign change from positive to negative, from negative to positive, and positive to negative? So the definition of Descartes' rule of signs is the number of positive real zeros is the same number of sign changes or less than the number of sign changes by a positive even integer. And this is very kind of wordy, but I think once you kind of apply it, it's going to make sense. You can also look at the number of negative real zeros by looking at the sign changes in f of minus x. And you always divide it, you always reduce it by an even integer. because they kind of come in pairs, right? So if I have 5 sign changes, then I either have 5, 3, or 1, positive 0. And that's kind of what this question is asking here. Determine the number of possible positive and negative real zeros. To do that, you have to check the sign changes in the function and the sign changes in plugging in minus x. What's minus x to the 5th power? Minus x to the 5th, right? Minus 6 minus x to the 4th power is just x to the 4th. Minus times minus times minus times minus is a positive, right? Right? So if I'm plugging in this minus x to the 5th is the same thing as minus x to the 5th. Here, since this is x cubed, this is going to be minus 12x cubed, minus 12x squared, minus 11x, minus 6. Right? You guys see how when I plug in a minus x to an even power, that makes it doesn't change the sign. But a minus x to a odd power will change the sign out front. So this odd power and this odd power and this odd power is going to change this sign, and this sign. You guys see that? So how many sign changes do I have in the function? In the function f of x? 1, 2, 3, 4, 5, right? 5 sign changes. How many do I have in f of minus x? 0. So that tells me I have 0 chances of my number being negative. Right? The roots are either positive, negative, or imaginary. Right? So 5, the reason why you think these come in pairs is because I know I have to have 5 zeros total. So if all of them are positive, then 0 are negative and 0 are imaginary. So I get 5 here. If one of them is imaginary, there has to be a pair, right? Because I can't just have one imaginary number because they come in the form a plus or minus bi. So if I need this total to be 5, that tells me that I have 3 cases. I have all 5 of them are positive, or 3 of them are positive and 2 of them are imaginary, or 1 of them is positive and 4 of them are imaginary. But in all the cases, I always have 5 roots, including the multiplicities. They might not be 5 different ones, but with the multiplicities, I have to have 5 of them. So that's what Descartes' rule of signs is saying. I'm either in this case, sorry, there's 3 cases here. I'm either in this case, or this case. So if I found 4 roots, I know the other one has to be positive. I have to keep checking that. This is just kind of a way to kind of check yourself. By Descartes' rule of signs, if I found 4, I know the 5th one has to be there. If I found 2, I know there has to be a 3rd positive real root. They could be, the other 2 could be imaginary here. It's very possible. But you can only ever have an even number of imaginary roots. And that's why you always decrease your numbers by an even integer. There's also ways to verify if roots are upper or lower bounds. There's not too much application here except to be able to confirm, yes, this is an upper bound, or no, this is not an upper bound. If you had infinite time on a test, you could test every problem, right? You could test every root. You could test every possible factor. However, it's not really realistic. So the application here is saying, determine if 2 is an upper bound. So if you have a polynomial with real coefficients and a positive leading coefficient, you have to have a positive leading coefficient. So if you divide it by x minus c, which is the same thing as plugging in c, right? Because the remainder theorem states the remainder is the same as plugging in c into the function. So if c is greater than 0, and if the remainder, both the remainder and the coefficients of the quotient are non-negative, then you can make the conclusion c is an upper bound. I've never really thought this had, too much application on a test. So I haven't asked these questions on the test, and I've never seen it on the final in the past. It's such a specific case. You have to, be able to test. However, it could show up on your homework on Alex, and you have your notes there, and you could say, okay, what does it mean to be an upper bound? If c is positive, and the remainder and all the coefficients are non-negative, so they could be 0, then you can conclude c is an upper bound for the polynomial. If c is less than 0, and the coefficients of the quotient and the remainder alternate signs, then you can say c is a lower bound. If those two things don't happen, you can't conclude it's an upper or a lower bound. So let's look at an application of it, because it's very theoretical right now. So if I'm looking at this polynomial, and I want to determine if 2 is an upper bound for the real zeros of the function. Because if 2 was an upper bound, I would be able to look at my possible roots, my rational root theorem, and say, okay, 2 is an upper bound, then all my roots have to be less than that. So I do the synthetic division with 2. 2, 1, 0. That's an important because there's no x cubed term. 9 minus 32 and 20. So let's see where this comes in at. So if I drop my 2, 2 times 2 is 4, plus 1 is 5. 2 times 5 is 10, plus 0 is 10. 2 times 10 is 20, plus 9 is 29. 29 times 2 is 58, minus 32 is 26. 26 times 2, 52, plus 20 is 72. C is positive, and all of the leading coefficients, or the coefficients in the quotient, and the remainder is positive, right? So this would be able to conclude that 2 is an upper bound. Right? So there's no zeros on the right side of 2. You guys see how that verified from the definition of an upper and lower bound? So if C is a positive number, it then becomes a candidate to be an upper bound. If you do the synthetic division or the long division, and all your remainder, or all your coefficients of the quotient and your remainder is non-negative, then you can conclude 2 is an upper bound. If C is positive, if your C value is positive, it's a candidate to be an upper bound. If you can plug it in synthetic division and these are your coefficients of your quotient, and your remainder is non-negative, meaning 0 or positive, then it's verified that it's an upper bound. 2 is an upper bound, 4 should also be an upper bound, right? So a lot of times you want to find the smallest upper bound. But 2 here, this would be an approach to this question. Can you verify 2 is an upper bound? To verify it's an upper bound, it has to be positive, and everything has to be positive. All the coefficients and the quotient and the remainder has to be positive. If you can show that, then you can say, yes, this is an upper bound. If one of these was negative, you would say, nope, it's not an upper bound. To verify something is a lower bound, the coefficients and the quotient have to alternate. Right? Coefficients and the remainder have to alternate signs. So either negative, positive, or positive, negative, positive, negative. If you have two positives or two negatives in a row, then you've not verified it's an upper or it's a lower bound. And you verify negative C values as lower bounds. So here, if we do synthetic division on -2, you have 2, -4, -3. So we're getting a good start. It would be 6, 6, -12, -3. 52, 72. So do they alternate signs? Yes, 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 no. Right, so here they do not alternate signs. So this is saying -2 cannot be a lower bound. So again, a problem like this is really testing, do you have that theorem memorized? And can you do synthetic division? So that's what you're doing. You're doing synthetic division, and then you're looking all coefficients positive. My C value is positive. That would be able to conclude that is an upper bound. If it's the C is negative, the coefficients have to alternate signs. If they do alternate, then you can confirm that is a lower bound. If we can bound them, like your notes were talking about when they first applied this Descartes' rule of sign, in this fifth degree polynomial, we can use the upper and lower bound theorem to show that all the roots are between -1 and 18. Furthermore, we can use Descartes' rule of signs that show none of the zeros is non-negative. So this eliminates all possible zeros except 1, 2, 3, 4, 5, 6, 7, 6, 9, 10, 11, and 15. Versus if you had all day, you could test all these. But by using these tools, you can start to say, I don't have to test anything above 18 because I know 18 is an upper bound. And you can say, okay, I'm testing 1, 2, 3, 4, 5, 6, 7. Get really good at synthetic division. We're almost right. I mean, a lot of these rules are used in computer science because you have a program. You program it to say, as soon as this happens, that's going to be your upper bound. So test this point, this point, this point, this point, and then it can do that for you. In the computation by hand, it's like not too useful to do on a test because you don't have 5 hours to take your test. So this next exam is going to test a lot, can you do synthetic division? Can you do long division? Can you come up with the quotient? Can you come up with the remainder? Can you come up from that? Can you do synthetic division again on the remaining quotient and come up with more roots? Can you tell me the rational root theorem? Can you list all possible roots? Things like that. So that's 3, 4. And at the last page, I just kind of print off some things that show up on Alex. For the polynomial below, 2 is a 0. Express h of x as products of linear factors. The linear factor products will be written as x minus c, x minus b, x minus d, things like that. Or c, b, and d are numbers. Right? This would correspond to c being a 0, b being a 0, and d being a 0. It's kind of backwards from if I gave you a unit factor and asked for the roots. Here I'm asking you to write it as linear factors. The fact it told me 2 was a 0, what's the first thing I want to do? If I plug 2 in, I get 0, because 2 is a 0. I have a third degree polynomial. I know one of the factors, so that means I have really a quadratic. How can I get that quadratic? I want to factor out an x minus 2. could do long division with x minus 2. Right? And if I can do long division with x minus 2, I can do synthetic division. Right? And it would be the same thing. 1 minus 6, 7, 2. So if I pull down a 1, 2, this would be minus 4. This would be minus 8. This would be 1, minus 1, minus 2, 0. If I did not get 0 at this point, I know I made a mistake somewhere. Because they told me 2 is a 0. They told me 2 is a 0. That means my remainder has to be 0. So at this point, I'm left with my quotient, which is x squared minus 4x minus 1. And I can set that equal to 0 and find its zeros. So I have x minus 2. That's my first linear term. And then I have x squared minus 4x minus 1. But I want every term to be linear. So I need to factor this. Doesn't look like it's going to be too nice. By the rational root theorem, it tells me my rational roots are plus or minus 1, right? Because my leading coefficient's 1. And my constant term's 1. If I plug in 1 or minus 1, I don't get a root. So that tells me I have to have either imaginary or irrational, like a square root. So I can always use quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So this gives me 4 plus or minus square root of 20 over 2. Square root of 20 is 2 the square root of 5 over 2. So this is 2 plus or minus the square root of 5. So if I wanted to write this as linear terms, I would have x minus 2 times x plus 2 the square root, 2 plus the square root of 5. Oops, that's x minus. And x minus 2 minus the square root of 5. So this is a little different on Alex, the way you have to kind of input that. On an exam, I would just ask for the factors. So you could write 2 and 2 plus or minus the square root of 5. If I gave it to you like this, it's clear to see that 2 is a 0, 2 plus the square root of 5 is a 0, and 2 minus the square root of 5 is a 0. This is it's factored in linear terms. You guys see that? This term is a linear term, this is a linear term, and this is a linear term. So on the online lecture, I will start here, and I will go over the Alex, and I might even pull up Alex and do some of the problems on how to input some of those linear terms. Sometimes the parentheses are important. No class on Wednesday. You're welcome to come in here and watch the lecture if you want. If you can turn it on. You can come over here, turn this on. If it's not on the PC, you can click PC because sometimes it's on different inputs. You could sign in, go to your Blackboard, and then the link will be in Blackboard. I'll also send you a link in as a Blackboard announcement, and we'll go to your email. And so you can watch it. The notes for 3.5 are already posted. I will continue on 3.5 on Friday. And then we'll do review. We do 3.5. The test is next Wednesday. So yeah, we'll do 3.5. I'll give you a review on Friday, and then we'll do that review in class. We'll finish up any questions, test on Wednesday, and then Friday, and we'll go on spring break.